Greetings to you all, and I would like to thank our organizers for granting me an opportunity to present to you this conference paper. Let's start with it. The paper is titled "The Use of Photovoltaic Energy to Minimize the Impact of Load Shedding in South Africa" by Dr. Mabunda, who is a senior lecturer at the University of Johannesburg in the Faculty of Electrical Engineering and the Faculty of Engineering and the Built Environment. I'm a professional technologist. Just to give you some background, the research was motivated by scheduled blackout which we have in the country from provinces down to municipality levels. And we also observed that most of our communities rely on the national grid. They can't generate power on their own from natural resources such as solar and the wind. It's made also possible by the cheaper prices of microcontrollers that we are using here to manage the energy. And in our objective, amongst other things which we'll cover, is how to build an energy load energy profile using an all energy logger. All is a company which manufactures electronic and electrical devices. Amongst other them, they've got an energy logger. So that becomes a useful tool for solar designers to study the load. We also used microcontrollers to manage energy by diverting connection from or between a low power solar source and high power grid source. We also evaluated whether, or we also studied, did some study to determine whether there is a link between load shedding and the number of houses that connect to the grid. We'll also check whether the low power standalone photovoltaic system can offer some form of benefits during load shedding. A standalone photovoltaic system that we used in our case, it can be presented using this block diagram. We've got an 80-watt roof mount solar panel that connects to a 10-amp charge controller, which charges a 50-amp-hour battery. And that battery powers an inverter which gives out the maximum power of around 350 watts. You see it's outlined right there. Our load consists of a router, a PC, and a 50-inch television set. So in our design, we never take into account the effect of dust, cable losses, and shadowing and so forth. The reason being that being a low capacity system as it is, should there be any serious effects of things like temperatures and the result of the power loss, one can easily increase the capacity of solar panel or battery bank without incurring more cost. For the same reason of this system being small, you'll see our equipment are small ratings. The battery, for instance, is 50 amp hour, and the panel was 80 watt as described. Now, this system is common. Most of you have seen it before. What is new in the research? It's quite often this is used to create primary power, not for backup. For backup, we use battery powered UPS, which are charged from the same electricity which they produce when there is no power. So I'll expect them not to last long, because here in the case when the sun is available and the battery is fully charged, you will get your energy directly from the sun. One of the key circuits here is a load diversion circuit that features a microcontroller that works in conjunction with a relay circuit. Its principle of operation is that at the input between a Zener diode and a current limiting resistor, you connect an interrupt pin. Now, this being 11 volt Zener, it will maintain a voltage of 11 volt across it. So if the input is 13.7, for instance, that represents a fully charged battery. The difference between 13.7 and 11 volts is 2.7, which will occur across the current limiting resistor and fed onto the interrupt pin. And the processor will interpret that as a high, and the interrupt is set. The rest is up to the software, which will send a command or give out voltage, output voltage, via the amplifier, which can be a transistor, to energize the coil of a relay. After being energized, the contacts of a normally open side of the relay get closed, which can thereafter connect the solar source to the load. Having that connected, the current will flow onto the load, give you energy up until the battery gets low, and then the inverter is shut down. But that will strain a battery. So perhaps you might have to consider using an analog input pin right there, which you will pull all the time to check the level of the battery. If it goes beyond benchmark, you switch off the unit and get ready for the next interrupt, which will start the charging process. If we look at what we accumulated in the all energy logger, the system was run for 2 hours, and we found that it supplied a continuous 2 watt without interruption. So in a sense, we had 240 watt, which was enough for those equipment mentioned. If you were in a Zoom meeting or busy with online classes where you use the computer and maybe a TV screen, there will be no interruption. So the impact of load shedding there will never affect you in any way. So which is during this time where there is COVID, people work at home, so they won't feel that much impact of the load shedding. But how will this stop the occurrence of load shedding itself? We studied the energy within a house when connected to a grid where everything is working. We've got geysers, stoves. The average power is about 3.3 kilowatt. When you compare it to the 240 supplied by an inverter, you find that you need 14 units of that standalone system to save one house from load shedding. So if 10,000 houses were disconnected during load shedding, so it means you'll have to have 140,000 of those units to stop the entire load shedding. Well, that is achievable if everyone can install the unit. But it is a fair comment to say within a smaller radius, you might have different weather conditions, especially during this time when we have climate change. So there, we capitalize on the fact that this is a smaller power system. So if the solar irradiance is not good. Battery banks can be easily adjusted than the PV sizes. Since it's small, you won't incur a major cost. And again, when you can't afford such kind of changes, and the solar irradiance is weak, you might have to scale down your load. Differences in load can be clarified by using example of a church and a school. Find that in a church, when there is load shedding, perhaps they might just worry about lights, as they don't use presentation equipment. The pastor read the Bible without presenting it. But at school, now they will think of projectors and laptops, which they use to deliver the courses. So there's a difference. But then the school will have an advantage of giving more relief to the grid, as it's going to consume more power from solar, opposed to the church. Which takes us to our conclusion. A grid power gives more power. That's obvious. But although the solar units design, they are of a less power. In numbers, they will be able to save load shedding. And also, whenever that occurs, you will be able to have a continuity usage of energy. So it shouldn't be a case of saying when you do a PV system is you want to like somehow cover everything in the house, but also to think that if we get to that bit, those energy you save collectively, they can like avoid load shedding altogether. I will be expecting questions from you, and you can go out and read the paper. This brings us to the end of the presentations, and I will say enjoy the rest of the conference.